Alright everyone, this is going to be the very last part of Unit 1. We're still talking about the atom, but now we are moving on to the current model of the atom that we actually use and focusing a little bit more on the electrons. So as you're watching this, make sure you're filling in the notes that you have, and then when we get to class on Wednesday, I will go over these with you and we'll do all of the examples at the end together. So I just need you to have the preliminary information ready to go. Alright, so to begin with, to review, we were looking at Bohr, Niels Bohr, if you remember. He came up with the last model of the atom we were looking at, and Bohr's model did a good job of explaining hydrogen and the spectral lines we were looking at. This is how we've been explaining where light comes from using Bohr's model. But the only problem with Bohr's model is it didn't really explain how other elements behaved. It worked really well for hydrogen, but it didn't work for bigger elements. So scientists knew that it was close, but it wasn't quite exactly what was happening inside an atom. So that led to a guy named Erwin Schrödinger. He was an Austrian physicist, and in 1926 he came up with a new model of the atom called the quantum mechanical model of the atom. And Schrödinger's model doesn't describe an electron's path. So Bohr said that electrons orbited the nucleus, right? Like the Jimmy Neutron orbits, the lines around that you see, or the rings that you learned about in middle school. So Schrödinger said that's not true. That's not what electrons do. Electrons can really move around wherever they want to move, in these spaces called atomic orbitals. So Bohr said that electrons orbit the nucleus. Schrödinger said that electrons can move wherever they want within these spaces, and the spaces, these three-dimensional regions around the nucleus, are called atomic orbitals. And this is where the electrons are most of the time. So the atomic orbitals don't have defined edges. So you can see the picture on the right gives you kind of a visualization of some of the different orbital shapes and where those electrons can be. But you'll notice they're not closed in because the electrons can move in and out of those spaces. These orbitals are where the electrons are found 90% of the time. So they look kind of like fuzzy clouds rather than closed-in balloons or something like that. Now, just like in Bohr's model, Schrödinger's quantum mechanical model is divided up into energy levels, and they're still labeled with the same description: n equals 1, n equals 2, n equals 3, n equals 4. But within those energy levels, they're now divided up into sublevels. The first energy level has 1 sublevel, the second one has 2, the third one has 3, the fourth one has 4, so on and so forth. And then the orbitals are those sublevels, and they have different shapes, and we use the letters S, P, D, and F to represent the different shapes. So S orbitals look like spheres. P orbitals, you can see, are kind of this dumbbell or bow tie shape, and there are 3 different ways that they're oriented. The D orbitals are kind of these cloverleaf shapes, and there are 5 different ways the d orbital is oriented. And then there's also an f orbital, and it's very complicated to look at. The f orbital has 7 different shapes that go along with it, so we don't really visualize or do a whole lot with the f orbital. So we have another kind of visualization of the orbitals, so you can see how they end up being stacked on each other. So here is an orbital in the first shell, so 1s, or the first energy level. Here's an s orbital in the second energy level. You can see it's a little bit bigger, and then the p orbitals all put together, and so that's kind of what it looks like once they start stacking on top of each other. And you're gonna notice it's gonna match up with the shells that you learned about in middle school. That's mostly accurate, but you're going to see where those numbers come from as well. So what we're going to do with these orbitals is we're going to write out what are called electron configurations. And electron configurations are basically just ways of describing those 3D orbitals where the electrons are found within the atom. So we're just coming up with a couple of different systems to describe these spaces where the electrons are found. And we have 3 rules that we have to follow in order to help define these electron configurations. And the first one is called the Aufbau principle, right here, Aufbau principle. And the Aufbau principle states that each electron occupies the lowest energy orbital available. And you can see over here, the lowest energy orbital is in the first energy level. It's an s orbital. So closest to the nucleus is lowest energy, and then it's going to fill up out away from the nucleus as the energy increases. The next rule is called the Pauli exclusion principle, and it says that only 2 electrons can occupy a single orbital, and they have to be spinning in opposite directions. So we represent the direction that they're spinning by using an up arrow or a down arrow for electrons spinning clockwise or counterclockwise. So the only way that 2 electrons can be in the same space is if they are spinning in opposite directions. And then the third rule that we use is called Hund's rule. And it says that electrons with the same spin will occupy empty spaces in the orbitals before they pair up. So in this diagram, you can see here that there are electrons paired up, but there's an empty space in this orbital. That's not accurate. Those electrons don't want to pair up if they don't have to, so they're going to occupy empty spaces when there are empty spaces. So from here, we're going to take a look at your periodic table, and we're going to understand how the periodic table is kind of like a guideline for helping us with these electron configurations. And then we're going to look at some specific examples with elements, and we're going to draw what those electrons are doing in the orbitals and how we can write out the electron configurations using the periodic table. So on Wednesday, make sure you have these notes, make sure you have your periodic table. This is where we will start in our discussion of electron configurations, and then we'll go through all of the examples together.